Project 2.6.1, The Tiny Clock by Atticus Toplady. The purpose of this project is to explore what the Inter-Integrated Communication Bus, I2C for short, is and how it works in relation to other systems such as the TC74 temperature sensor. There are two devices connecting to this I2C bus that helps demonstrate the code developed. Those are the DS1307 RTC and TC74 temperature sensor. The DS1307 RTC acts as a small clock while the TC74 acts as a temperature sensor. The TC74 chip is a serial access digital temperature sensor. Pins 2 and 4 of the two pins that connect to the TC74 to the microcontroller. These are pins 2, which is the SDA pin, and pin 4, which is the SCLK pin. The DS1307 chip is the fundamental backbone to how this low-power clock works. Pins 1 and 2 on the DS137 chip are the two pins that connect to the 32.769 kHz crystal, while pin 3 is the pin which connects the battery's power supply to the 3-volt CMOS battery needed. Pins 5 and 6, the D137 chip, are the two pins that connect to the microcontroller through the data and clock line. The data and clock line, SDA and SCL for short, are what drives I2C's communication. The SCL clock pulses high and low in order to drive the sending and receiving of bits, while the SDA data line contains the value of a sent or received bit during clock line transmissions. A single pull-up resistor is used on each line to connect the SDA and SCL to a 5-volt power line. This is required since the SDA and SCL connections on the devices are open drain lines, meaning that while they can drive the voltage on the line to 0 volts, they are unable to raise it to 3.3 volts. The I2 bus is successfully able to locate each device with the chip's respective address. I2C addresses are usually 7-bit numbers, so a bus can comprise up to 127 devices in all. Addressing is when the circuit is able to detect the location of a certain chip by finding a chip's internal address, which is different from every single device type. The data protocol of the I2C bus is put into 3 sequences of 8 bits, as the diagram below depicts. The circuit will initiate the start command once the SCL line is high and the SDA line is low. After the start command has been called, the clock starts and each data bit is transferred during each clock pulse. Following the first 8 bits in which the circuit locates the address of each chip, there is an acknowledge bit. After the acknowledge bit usually comes a second sequence of 8 bits in which the circuit attempts to detect and read the internal registers for each chip. Following the second sequence of 8-bit reading, the circuit yet again implements an acknowledge bit before moving on to its last read of the final 8 bits. After the addressing bit, the data transfer sequence begins either from the master or slave, depending on the RW bit. The start command is initiated after the data is completely sent and occurs when the SDA line goes from low to high while the SCL remains high, the inverse of the start command. The code implemented uses the library wire to detect the locations of each device. The code is set up in a way that every 5 seconds the code will rerun what has been set and detect the number of devices still attached to the I2C bus. The wire library is accessed through the use of wire.begin and wire.end commands, which will start and stop the code when locating each device. When removing one device, the code will respond to that through the implementation of the loop function. This code seems quite complicated, but it utilizes common concepts such as the if command, for command, and serial.print command. Thank you for taking the time to listen to my video on the tiny clock.